Okay, in this example we have an indeterminate form of 0 to the 0 power. We're going to see how we deal with that. Again, with all of these examples of having x in the exponent or having a variable in the exponent and evaluating limits, we're going to first take the natural log and work with natural logs. So let's see how that pans out. So we have the limit as x approaches 0 from the right of sine x to the x power. And you recall that as x approaches 0 from the right, sine of x, which looks something like this, as x approaches 0 from the right, sine of x will also approach 0. And since the exponent is approaching 0 also, we're going to have a form of 0 to the 0 power, which is an indeterminate form, but it's not one of the forms that we can deal with directly. So we're going to assume that the limit exists, and we're going to set it equal to y, like so. Then the next thing that we're going to do in these cases always is that we're going to take the natural log of both sides. And you can't forget to take the natural log of both sides. Then, because we have the natural log of something to the x power, we can rewrite that by bringing down the exponent. And so we have the limit as x approaches 0 from the right of x times the natural log of sine of x. Now if we were to plug in 0 into that, we'll get 0. Now sine of x is approaching 0. We've already demonstrated that above. But the natural log as sine of x approaches 0. Since sine of x is approaching 0, then the natural log as sine of x approaches 0 is actually going to negative infinity. And so what we end up with here is 0 times infinity. Actually, it's 0 times negative infinity. But 0 times infinity is an indeterminate form, but still not something that we deal with using L'Hopital's rule directly just yet. And the way we got around that, or the way we prepared it, was by, instead of multiplying by x, we'll divide by 1 over x. And now we're going to get ln of sine x as x approaches 0 from the right is negative infinity, and 1 over x as x approaches 0 from the right is going to become positive infinity. And so we end up with an infinity over infinity, which is something that we can use L'Hopital's rule for. We take the derivative of the numerator, which is 1 over sine x, times the derivative of sine x, which is cosine x, divided by the derivative of 1 over x, which is negative 1 over x squared. So the numerator is going to give us cosine x over sine x, which is cotangent of x. And you recall that cotangent of x is really 1 over tangent of x, and negative 1 over x squared in the denominator can be rewritten as negative x squared. So we can rewrite this whole thing as limit as x approaches 0 from the right of negative x squared over tangent of x. But once again, or this time, we have a 0 over 0 indeterminate form. And that allows us to apply L'Hopital's rule a second time. Now this time, the derivative of negative x squared is negative 2x. And the derivative of tangent is secant squared of x. And this time, plugging in x equals 0, we're going to get 0 in the numerator and 1 in the denominator, leaving us with a limit of 0 at this point. So it can be evaluated at that point. But again, remember that this 0 just means that the natural log of y is equal to 0. And that means that y is equal to 1, and y is the limit of, as x approaches 0 from the right, of sine x to the x power. So our answer here is actually 1. And that does it for this example and for this video.